In the previous video, I described how the Zener diode works and went further to explain what breakdown voltage means, which is a key thing to note to help you understand the content of this video. In this video, I'll show you how the Zener diode can be used to build a simple linear voltage regulator. Let's get into it. We'll start by connecting a load to a voltage source. Now this load requires a voltage that is significantly less than what is currently attached to it. One way to reduce this voltage will be to change the voltage source entirely. Although that would definitely solve the problem, in most practical cases the source voltage is a rectified AC signal from the mains to our device. Another way will be to reduce this voltage, and since we're talking about a Zener voltage regulator, we will add a Zener diode in parallel with the load. The Zener diode must be in reverse bias for us to make use of the Zener effect in the diode. If the diode is connected in forward bias, the two terminals of the source will be short together. This will not only be catastrophic, but would also prevent current from flowing from the source to the load. This is the circuit we have at the moment. The Zener diode, reverse biased by the source in parallel with the load. The Zener diode in the regulator is meant to force a voltage which is equal to its breakdown voltage onto the load in the circuit. But currently, the presence of the voltage supply will force the voltage across both the diode and the load to go back to the source voltage, which ruins the purpose of this circuit. To counter this effect, we need a way to limit and divide the current and voltage and send only what we need to the load. We accomplish this by introducing a resistor right after the voltage source. That way, the load will receive the required voltage. But how do we determine the size of the resistor? If you're finding this video valuable, hit the like button, and also I make electrical engineering explainer videos like this one, and so subscribe and hit the bell for notifications so you never miss a video. Let's get back to it. So I explained how we're supposed to introduce a resistor to limit the current and voltage flowing through the diode. To determine the right size of the resistor, we need to find out the minimum and maximum current limits of the breakdown region of the Zener diode. This information is mostly found in the diode's datasheet. A quick Google search for a commercial Zener diode led me to find the 1N4728A Zener diode. We can find the maximum Zener current in the absolute ratings section. As we can see here, the maximum Zener current should approximately be the total power PV divided by the Zener voltage VZ. The Zener voltage VZ is the same as the breakdown voltage, and from this data sheet we can find it to be about 3.3 volts. Since we're not sure of the total power in the circuit yet, we can simply use the maximum current allowable by the diode, which is 276 milliamps. Now that we know the maximum current allowed, we can use this value to size the resistor. The resistor needs to be sized in a way that first of all gives the desired output at the load and also limits the current that flows through the diode. I'll illustrate this with an example. Say we have a simple Zener voltage regulator here with a 2 kilo ohm resistor load attached. We wish to have 3.3 volts across the load from a 5 volt power supply. Since a 3.3 output voltage is required, the Zener diode must have a breakdown voltage of 3.3 volts. Also, since the source voltage is 5 volts, the voltage across the current limiting resistor will be 5 minus 3.3, which is 1.7 volts. Let's assume the current limiting resistor has a resistance of 340 ohms. That means that the current flowing through it will be 1.7 divided by 340, or 5 milliamps. We know from KCL that the current splits when it gets to this node. The current flowing through the 2K load is 3.3 volts divided by 2K ohms, or 1.65 milliamps, leaving 5 milliamps minus 1.65 milliamps. That is 3.35 milliamps as the current flowing through the diode. As seen earlier on, the diode had a maximum current of about 276 milliamps, and therefore 3.35 milliamps is well within range. And that's it, we just designed a Zener voltage regulator with 3.3 volts as the desired output. Let me know in the comments which topics you'd like to see explained on the channel. Thank you for watching this video, and I'll see you in the next.